Hello everyone, so I hope you are doing well. In this video, let's talk about another type of photochemical reactions, which is hydrogen abstraction reactions, right? So in our previous video, if you remember, we have talked about the Norris type 1 reactions, right? I hope you have watched it. Like if you want to know about more, otherwise how to introduce a reaction mechanism for a particular problem, I highly recommend you to go back to that video and watch it. I will put the link here, right? Now let's move on to the reaction. So in this case, I will explain to you this reaction mechanism from an example. Let's take a carbonyl group, right? Here we have a carbonyl group. Now every time when we are talking about a particular photochemical reaction, we need to consider the excitation. So first step, what you need to mention in your paper, otherwise in your answer, is the excitation process. So here we have the carbonyl group. Now it's excited. Always remember, you need to mention the energy states. Like it can either S1, which is singlet excited state, and you can see there are no pi bonds. There's an oxygen group, which means the transition should be N2 pi star. We have talked about these transitions and excited states in our previous videos, right? You can watch the transitions in our playlist. You can go to our playlist and search for transitions. There is a particular video for how to identify a particular transition. Now for now, let's go with the flow, right? So here this excitation can happen through either S1, otherwise singlet excited state, or triplet excited state. It is also N2 pi star transition. Okay, now our molecule is excited, right? Now when the excitation happens, the electron transition happens from N, which is the non-bonded electron orbitals, to pi star. Now this N orbital, otherwise this non-bonded orbitals, are positioned in the oxygen atom, right? Because we are considering these non-bonding electrons. These are the electrons which are going to be excited. So this N, otherwise this non-bonding orbitals, positioned on our oxygen atom. Now when the excitation happens, you can see these electrons, these excited electrons, are going towards the pi star orbital. If I ask you where does this pi star orbital position, right? You need to know that pi star orbital is positioned for both oxygen and carbon. This is a bonding orbital, right? Otherwise this is an anti-bonding orbital, right? So this anti-bonding orbital is positioned for both oxygen and carbon. It's based on this bonding process. So now our oxygen's electron density is reduced when this transition happens, because initially the electrons are on the oxygen atom, right? But now when the transition happens, these electrons are a little bit moved away from oxygen into this bonding nature, otherwise this antibonding nature. This antibonding nature is belongs to both carbon and oxygen. This antibonding orbital, this pi star orbital, is belong to both carbon and oxygen. Now when the transition happens, the electrons are now in this particular orbital, which means the electrons are moving away from oxygen and coming into a middle position like oxygen and carbon. That results in electron deficient oxygen. Now this is important, right? This is important for our mechanism. Let's say I have introduced a substance like this, which is an hydrogen, or otherwise hydrogen donating substance. So this can donate hydrogens, right? It can release hydrogens. Now what happens? This bond right here is weakened due to this transition. Now we can introduce our mechanism like this, and this bond breaks into here, this one breaks into here. We have our two products like this one. Here we have the oxygen and hydrogen, and remember this electron comes to here, plus these electrons come with the X. These are radical mechanisms, right? These are radical mechanisms. These are our intermediate products. These are our intermediate products. Now, very important thing, right? The basis of this mechanism is this one. You need to get full understanding of about this. Like, why did hydrogen comes with contact with the oxygen, right? You need to be able to explain what is this process and how this transition affects our reaction mechanism. You must be able to explain it, right? I hope it's clear to you now. So let's continue with our reaction to see what happens after this process. So these are two radical pairs, one otherwise our intermediate products. Now another small thing which you need to know about is, I have told you that this process, this radical mechanism happens through either S1, which is the singlet excited state. This is the singlet excited state. Singlet excited state, or the triplet excited state. Now my question is, why triplet excited state, right? Why triplet transition? Otherwise, the triplet excited states shows more efficiency or more feasibility. Why this happens? So actually I have talked about this particular point in our previous videos also. If you have watched the video, you must be able to come up with some reason for this this statement. Why T1 or otherwise the triplet state is much more feasible, much more prominent in these reactions. Okay, so pause the video and think it, right? Just draw the energy diagrams, I mean the energy states, draw the intersystem crossing and see what's the reason for it. Now I will explain to you, right? So here we have the ground state, which is the singlet ground state. Now here we have the singlet excited state. Okay, here we have the triplet excited state. Now when we go through the process, okay, when the photolysis happens, our electrons is in this position. When light is being absorbed, our electron get excited into high energy states, which is the singlet excited state. I hope you know that this excitation, this process, this yellow color process is not happening, right? S0 to T1, this is not happening. This why? This is spin forbidden transition. This is spin forbidden transition. But this one, S0 to S1, this is allowed, spin allowed. So this happens, like this transition S0 to S1, this happens in very high rate. Okay, this has very high probability. While the S0 to T1, this transition has very low probability. So we can neglect the whole process which comes from S0 to T1. Now after this S1 is occupied, after this transition happens, okay, two processes can happen to relax our electrons. Either it can come back into the ground state, which is much more feasible one, otherwise much more allowed one, because S1 to S0, which is spin allowed. S1 to S0, this transition is also spin allowed. Otherwise, as intersystem crossing. Intersystem crossing can happen to populate the T1 state. I hope you remember these things. We have talked about this intersystem crossing in our first videos in our series, right? Now when you have occupied, otherwise when you have populated this T1 energy state, otherwise this T1 excited state, in order to get relaxed, you have to do the transition which is T1 to S0. Now if you look at this very carefully, you will see this is spin forbidden, right? This is spin forbidden. This is spin forbidden. So this transition has very low probability. So what happens due to this very low probability? Our electrons, right? Our electrons in this particular T1 states stays for much longer. If you compare a lifetime in this S1 state and T1 state, the lifetime in the T1 state is higher. Why? It cannot get relaxed because this transition T1 to S0 is been forbidden. So he has to stay for a while in order to get a proper time, or otherwise a proper situation to get relaxed. So it will stay more time in this T1 excited state compared to S1. When you have an electron on the S1 excited state, he has a direct path. S1 to S0 is been allowed and it's much more easier. So when you have this electron, it will quickly go down back to the S0. But in this case, T1 excited state, this electron cannot go back into the S0 at very quick rates. That's why our T1 excited state has relatively higher lifetime. This symbol is tau, right? Tau, this is meaning the lifetime. Now, what happens when you have higher lifetimes, right? You know, when it comes to a reaction, right? When it comes to a reaction, you need these molecules to collide with each other. Otherwise, you need to have some interaction between these reactant molecules in order to go through a reaction. So when you have S1 excited state, right, you have already been relaxed when the collision happened. You don't have enough time to go through with the mechanism. Why? Your electrons are going back into the ground state before the molecules come into contact. But when you have T1 excited state, these having a good lifetime, otherwise higher lifetimes. So when the collision happens, the electrons are still in the excited state, right? Because they have a high lifetime, so they can continue with the reaction mechanism. That's the proper answer. I hope you get the idea, right? Get the idea, understand the concept, then you can handle the answer. So I hope it's fine for you. Now let's move on with our mechanism. So when here we have talked about the hydrogen abstraction reactions, right? So when this happens, right, there are two variables, otherwise 2 points which determines this reaction. First thing is the bond strength of this HX. Otherwise, we are calling this as bond strength. I mean, like the strength of the bond broken. The strength of the bond which is being broken. And the other point is the strength of the bond which is formed, which is the OH bond. Strength of the bond which is formed. These two are the main points. Otherwise, the main factors which affects our particular reactions. So, have a little memory about these 2 points. So you will see that when you have a very good hydrogen donating substance, this bond strength is lower. When you have very low bond strength, you can break this bond much more easily and bind this hydrogen to our oxygen easily. So what are the most good electron donating substance? If you have an alkene, right? If you have an alkene, these are very good electron donors, like CH2H. This hydrogen over here. This hydrogen. This hydrogen is a very good electron donor. Why? There's a pi bond, so resonance stabilization can happen after the breakage of this bond. Amines are also good hydrogen donors, and then we have alcohols. Alcohols are also very good. Let's do some examples, right? Let's do some examples with this alkene substance to see exactly how to arrive at particular reaction mechanisms. Okay, how about this one? Let's take, we have an ketone, okay, and we are going to react it with this toluene. Here we have toluene. So I will put the hydrogen here like this. Now first step, what happens is the excitation, right? So this is our chromophore. This will get excited. Here we have an excited ketone. Always remember to mention the excited states, right? S1 singlet excited state and N2 pi star, T1 N2 pi star. Then what happens? This hydrogen is going to be broken. How we can represent it? Always remember, these are radical reaction mechanism. Sorry, these are radical reaction mechanisms. Okay, so you have to always draw the half arrows like this. So here we have the other one. We have our products like this, R2, R1. Here we have a radical, and when it comes to this toluene species, we have a radical on this place. Okay. Now what happens after this initial process, right? After this initial process, what can happen is a coupling process. These two radicals can come together. We call that as a coupling. Okay. Which gives a structure like this. Okay, this is coupling. So let's take another example, shall we? Final example. The same ketone, let's take the same ketone with this one. Now we have only 2 pi bonds and we have 2 hydrogens over here. Okay. Now the first step would be like the same, right? So here we have a pi bond. So if we can remove a hydrogen, the rest species can be stabilized easily through this resonance. So the first step, I will skip that excitation part. Okay, so normally you have to draw that excitations part. This one I will skip this, so otherwise the video would be much longer. Now here I'm going to draw the 2 radical reactions coming together. So this one is going right back here, and this one coming right back here. Now we have R1, sorry, R1, and here we have the oxygen, and here we have the hydrogen, which is being removed from this particular bond. Now we have here R2, and we have a radical in this on this carbon position. Now in this case we have our ring structure like this. We have a radical in this place, and we have a hydrogens also. Now, as I have told before, there are 2 possibilities which we can go through. First thing is we have talked earlier in our example, which is the coupling. A coupling can happen through this one comes together. So what happens? R1, here we have an OH, and here we have our ring structure. R2 is here. The other one is the disprotonation. We have talked about this disprotonation in our previous video. We have talked a lot about this disprotonation. Now, in this case, what happens? Let me erase this mechanism. Okay. Right. Okay. Now, in disprotonation, what happens? This hydrogen over here, right? This one will come into the contact with here. So here we have a radical, here we have a radical. It will come together with this bond's radical, and the other one. Let me take another color. Let's say, right. So here the other one will come together to form here. Now we have our R1, OH, R2, and here we have an hydrogen. This hydrogen is the one from here. This hydrogen is being removed from this bond to bind with our carbon in the middle. And now this bond, right here, look at this bond. This bond is being broken into 2 radicals. So one is the hydrogen and other radical is coming together to pair with this previously formed radical. Now we have our ring structure like a benzene. This is our newly formed pi bond through this coupling. Okay, so this is this protonation. Okay, this is this protonation. You cannot this is the proper way, right? This is the proper way, but it's not it's not that much feasible if you if you break this particular bond. Like, I mean, there is a possibility, like you can draw the mechanism from here, it's fine, but it's much more feasible and it's much more acceptable if you draw this hydrogen to be removed. I hope you get the idea. So this is the hydrogen abstraction reactions. We have talked about a little important details, especially in this case, this point, right? I hope you get the idea. If you have any problems, please feel free to comment below. I will try my best to answer those questions. So in our next video, we will continue our discussion about the photochemistry.